The first type of unconventional gas that we're going to look at is something we call tight gas, or also shale gas. They're really the same thing, although they're kind of different extremes, although we recover them with the same process, so we can have this discussion. Here's an interesting diagram that has a little pyramid of unconventional gas. The middle one, coal bed methane, we're going to talk about that kind of separately later. But here we're talking about tight gas and shale gas. And the primary difference, again, as you can see here, is these units called MDs, right? It has some numbers over here. Well, again, without getting into the kind of nerdy hydrology stuff, that's a measurement that communicates the permeability or the hydraulic conductivity of that material. So if you were to imagine a sand, actually there's some photomicrographs over on the left-hand side. You can see the upper portion, conventional oil, lots of pore space, good hydraulic conductivity, permeable, right? All of the little pores, fluid can flow through there pretty easily. Hydrologists use this a lot to talk about water, right? So how quickly groundwater can move. In this case, we're talking about hydrocarbons moving, and they need to move because we want to pull them out. Fundamentally, if we put down a well and we're extracting at that well, if the oil can't flow through the formation to the well, it's not going to work very well. Totally unintentional, but I think that was a good joke. So again, fundamentally the problem here is grain size, right? This material is too fine-grained for these hydrocarbons to flow through. So we have to go after it, and that kind of brings up a big political issue, something that we hear about all the time, and this is the process of fracking or hydraulic fracturing. In the case of tight gas, which is going to be the first unconventional oil, or unconventional gas, excuse me, we're going to go into, as we saw in the last segment, it really has to do with permeability, right? So the ability of material to flow through a particular rock unit. So again, just kind of reviewing some of this stuff. If we have an environment that has a high enough organic flux, right, remember all of those fats and all that stuff settling down into the mud layers. Well, if those settle in sandstone or coarser grain material, they'll flow out, but if they're in really fine grain material, they're basically stuck. And that's where the term tight gas comes from. The rock is essentially packed really tightly. And you can actually see, again, we talked about tight gas and oil shale. They're basically applications of the same thing. So again, here you can see the triangle diagram that's showing tight gas is not as tight as shale gas. And then also here's an illustration that you can see basically the same thing in a diagram form. Over on the left we have maybe some sandstone or something that has a very low percentage of pore space, so tight sandstone or maybe like a siltstone. And then down on the bottom it's showing shale. The method is basically the same in either of these cases. So the problem, remember, is all about flow. Of these hydrocarbons within that unit. And so if we were to install a well in a traditional way, we'd be able to extract gases just from the area immediately surrounding the well, right? So kind of in this zone right here. But because the pores are too small, no gas can flow in. So we're going to fix that problem, and this is kind of part of the natural gas revolution. Again, we employ some directional drilling techniques. We have a few little instruments that kind of sit behind the drilling head of the well drilling. Remember that little bit that we talked about? It can kind of drive through, make sure that you're staying in the same shale unit. And again, we've actually seen this before in the case of some other oil. We would, you could maybe go out a kilometer. You can go pretty far. That's about half a mile. And we would see this spread out in kind of a spider web fashion, where there would be one central kind of vertical structure, and then it would spread out again like a wagon wheel in 2 dimensions. And so actually when we look at an area where we have these types of gas development fields, we see that generally they're spaced about every square kilometer. There's a new spot. And the reason is gas has very low permeability, so it can't flow from farther out in the reservoir like it would in the case of oil. I've drawn a blown up version here. We'll actually look at a more professionally drawn diagram, but I wanted just to give you the nuts and bolts of how this works. So we install our well, right? We dug it horizontally with these cool little machines that can drive the head of the drilling rig, and we inserted casing, right? So there's a metal casing in here. One of the things that's going to become an issue in the case of fracking is that casing is then packed with essentially clay, or in some cases concrete, and that's supposed to act as basically what they term a grout. And so hopefully that provides this like protective barrier. Then they actually use something called a perforation gun, which is inserted in the well and basically blows holes in the well casing itself, and that's going to allow us to actually frack the material. So in this case, we would insert a tool here called a perforating gun. It would, by the case of small explosions, it basically blows holes in the casing itself. So that's how our well casing gets perforated. Now we have well casing that's like Swiss cheese, full of holes in an orderly fashion though. And at that point, that's when we bring in the fluid, the hydro and the hydrofracking. And we take a mixture that's mostly water, but you're going to see this is going to kind of become a point of contention a little bit later. We take this mixture of water, run it down into our well, and just keep pumping more and more and more in. The well has a solid cap, and so the pressure rises and rises and rises, and that fluid gets to really high pressures, and it starts to pop open the rocks at these locations where the well casing is perforated. So we've actually kind of met this concept before. What we see is that as that fluid pops open one of these fractures, see here, that's what my drawing is showing. My pen is starting to run out of gusto here. I might need to switch pens. So this fluid will pop open our surrounding rock. That's the fracture part of fracking, right? So, but just as you can imagine, eventually we have to take this fluid and get rid of it, right? Because we've got this thick, kind of gooey fluid that's been shoved in here to pop all the rocks open. Well, before our well's going to work, we got to pull that fluid out so that the gas can flow out. Now, if we do that, we don't kind of add any scaffolding, all of these fractures are just going to close back up. So one of the most important parts of this fracking fluid is that it has sand in it, or again, little ceramic balls, but sand is way cheaper. And so those grains of sand sit in here and hold these fractures open, so that later, when we take that fluid back out, these fractures are now held open, and those gases will flow out our well, and we can kind of provide a suction and pull those gases off the top of the well and package that material and sell it, take it to market and sell it. So you can see here, this is a diagram that kind of shows you what I was attempting to draw over the last few. So you can see, first of all, we've got directional drilling that occurs, then we have casing that's applied, then we have our perforation gun, and then we have our fractured well that gas will now flow out of. Well and good, right? And actually on paper it all sketches out pretty nicely, or it all checks out. But as you know, especially if you've paid attention to the news over the last 10 years, it's not quite so simple, and it doesn't always work so cleanly. One of the primary problems with fracking, or hydrofracturing, if we want to use the proper term, is again, we've now perforated the well casing, and we've fractured our rocks, we've injected sand and all of that. And the thing that did that for us was this fluid. So I mentioned it's water plus. So we actually add all sorts of things to that water to make it work better as a fracking fluid. So first of all, We needed to move sand. So water doesn't move sand very effectively. We add some materials to it we add some compounds to it to make it a little bit thicker. If we want to do this process in the winter, we can't have our fluid freezing, so we add some alcohols and things to it to make it so that it has an antifreeze component. We want the sand grains to all move around really nicely, so we can add some lubricating agents to it. So you can see here, this is a diagram that shows some of the kind of general groups of chemicals that are added to this fracking fluid. So there's a reason why we don't call it fracking water, right? It's water plus all kinds of other things that make it work better for this purpose. When our fracking process is finished, I'd mentioned before that at this point we need to take the water out. And that's where we run into our first problem. What the heck to do with this water? So as this water comes out, it's got to go somewhere. And we also know that it has some chemicals in it that aren't the most friendly. So there's two ways that we see this dealt with. Well, there's a few more than two, but there's two primary ways. One of the ways is to take a pond, make a pond, line it with some thick rubber lining, and just store the fluid there for later removal and treatment. So we do have some ways that we can chemically treat this stuff. So these ponds, are great for the short term, but again, storms and heavy rainfall events and other things like that can actually spill over or cause the ponds to fill up and flood. You could have the failure of one of the berms. So a spill is a possibility in this case. The other thing that we do, and this is, some people have a hard time imagining that this is legal, but it is. We take that fluid and we use what's called an injection well. So this is near to where our fracking is occurring, but the well is much, much, much deeper, sometimes an order of magnitude deeper. It's way down in the earth. We pump that fluid way, 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 way down, out of sight, out of mind. Again, that's a little bit crazy. One of the things that we've seen as a response or a kind of geologic result of increasing what we call the pore pressure, or the pressures inside of rocks by adding fluid, is we've seen injection well related earthquakes spike, right? So somewhere like Oklahoma, geologically, shouldn't have earthquakes. It's in the middle of what we call the stable North American craton. There's no plate boundaries, there's not a lot of geological stresses. Well, there's always a little bit, but once we started injecting this wastewater, we now see that there's a significant seismic hazard. Now, this is a USGS seismic hazard map, and if you look at Oklahoma, and that's all man-made, right? That earthquake hazard was not there 15 or 20 years ago prior to using these injection wells. The other really big problem for this fluid is the stuff that's in it. So we'll see how well I do stitching these two images together. But in the United States, one of the big issues is we basically have had someone show up with briefcases of money, set those out on the table in Washington, D.C., and say, I don't want to tell anyone what's in my fracking fluid. And our lawmakers said, sure, I agree with you. You don't have to tell anyone what's in your fracking fluid. So there's a law in the books. This is a proprietary mixture as seen by each company because that's what makes them profitable. They came up with their own concoction, and legally they don't have to tell anyone what's in it. So that's a pretty big problem, right? And so when it comes to changing the perception about fracking and natural gas extraction, that's a really good place to start. So in the US, there are about 750 different chemicals that are commonly used. You can see here's a list just off of Wikipedia, and like I said, I'm just going to stitch a few of these together and not give you the exhaustive list, but you get the point. We use all kinds of different stuff, and none of it really has to be approved, and nobody knows what you're using. So there's a significant problem with transparency. In parallel, we're not the only country who extracts gas this way. We're not the only country where fracking happens. An example would be to look at the UK. And so in a place like that, they have much stricter control governmental control and environmental regulations on what you can use. So here, in comparison, this is a list of what a company that's doing hydraulic fracturing in the UK can use as an additive to their fracking fluid. This is a pretty small list, right? And so we start to see, what the heck is going on here, right? Is that really needed? So taking one step back and thinking about this wastewater in the pond, or this water that's injected deep into the earth, we really have no idea what's in there, although we have a pretty good idea of what types of chemicals are in there. I drew a diagram like this earlier, actually, when we were talking about well drilling. Here, gas kind of works the same way, and this is where we're going to see the last real problem that we run into with natural gas extraction, and it has to do with the way that these wells are set up. So remember, this is geological material, right? But the Earth's not incredibly stable, so we add well casing, which is the steel tube. And again, you can hopefully recall that it kind of works like one of these telescoping antennas, right? So it's different pieces of well casing inside of one another, and so they're inserted down into the well. And for that to work properly, it's really important that those different segments be seated properly. So if they're in here at any wonky angle, there won't be a seal formed at those different joints. And really, that's something that's pretty hard to tell if you're installing a well, right? That's really just kind of method, and could be situationally, maybe they're misaligned just by a little bit. You might not know that, and so that seal won't seat properly. Outside of that, we also talked about filling this gap up with a clay material or concrete, but oftentimes a clay called bentonite clay, which functions as a grout. That clay grout material is intended to prevent leakage or loss of any material if the well casing is not seated correctly. The problem is, it's nearly impossible to tell if there's an air bubble or an air pocket in the grout itself. And if those two things are coincident, right? So if there's a misaligned section of well casing and also an area that's not properly filled with grout, or fractures in the grout or thin grout, you can lose material, right? You can lose whatever you're extracting from the mine. In this case, it's natural gas. If the surrounding rock here is hosting groundwater, so groundwater is the water that we drink, right? The water that comes out of your tap doesn't come out of the Boise River. It comes out of the ground, largely. So if this gas is leaking into a body of water, it can, in a very real way, cause contaminated groundwater. One interesting thing that happens is when we look at groundwater contaminants, some of them don't mix with water, right? Oil and water famously don't mix. Ask the Canadian tar sands people, that's how they extract it. But here, these gases will actually float and sit on top of that package of groundwater, and if you're running a well and you're pulling your water up, you'll pull kind of gas off of the top of your well, and then after it runs for a while, you'll get down into the water. It is important to point out that if there is natural gas in an area that has groundwater, that can happen with no intervening at all, right? If there is naturally occurring gas and it's fluxing up through the rocks, it can hit that groundwater, get dissolved in the water, and concentrate up at the top and burn, right? These famous instances of people, setting their tap water on fire. There's lots of places you can do that don't frack. But that's not to be diminutive or dismissive of this process. So this is a very real cause of contamination, right? So the groundwater contamination that we're concerned about. Although in this case, it's contamination with the gas itself, rather than what we saw on the front end, which was the fracking fluid itself being the problem, right? Whether it's stored in a pond or deep well injection. So there's quite a few ways that this can go wrong. Again, the thing that's important to struggle with, or that I hope that you struggle with, is this notion of, well, is switching to natural gas better? It's less CO2 in the atmosphere, but potentially concentrated pollutants, right? As we see natural gas displace coal.